All right, that should be good. All right, so then the last thing, coding challenge 6 is due Saturday at 11:15. It's due at noon. I'll monitor this Slack on Friday and Saturday. I wanted to make sure that I picked that date specifically because I know if it goes too much further past that, you start bleeding into the logic design exam, and you start bleeding into that, you can use the time for, what's it called? System. So I wanted to make sure it's in the middle. One thing regarding the self-service extension for this assignment, it will be 2 days instead of 1 because the self-service extension would push into Easter. So the self-service extension, I'll make sure that's set up. I don't want you to do on Easter Day at a Catholic school, well, anywhere, but especially a Catholic school, don't want to do that. So we're going to make it Monday. So if you get that extension, you can use it. Does anybody have any questions about anything that's upcoming? So I don't have anything on mute and I don't have anything there. So anybody have any questions? All right, so let's get started. And what I'm going to do first, in the code that you have been provided for lecture 16, if you run make prob 1, it'll give you this problem. So I want you to take a couple of minutes and see how much you understand about depth first search, and we'll go over the solution together and we can see the principles of recursion and the principles of hashing to be able to determine whether or not we can go to a specific node when we run that. So please take a couple of minutes to work on that problem, and then afterwards I'll go to the whiteboard and I'll work through the solution. Okay, so quickly, who wants to tell me the correct answer? Did you know it? Yes. C is the correct answer. So let's walk through this and determine why C is the correct answer. So if you see that, you'll have 25 towards it. So on the whiteboard, what I'm going to do is we are going to walk through it step by step. So now everybody should see the whiteboard. Nope, it's on the wrong screen. That's wonderful. Cam. There we go. Okay, so here's a step-by-step. So we start at node 0, and the way it works is that the order in which it's inserted is important. So there's no guarantee that we're going to get everything in a nice, clean order. So what happens is we see that it has 0, 3, 1, and 2. So the two things we need to bear in mind is we're working through this. We're going to say a recursive stack. And then we're going to say, we're going to have a mapping of visited and parent. So what's going to happen is we have 0 and we start there, and then we move to 3. So now what's going to happen is we have 0 with its parent is -1. And then we have 3 here, right? So what's going on is we have now checked 3 out first. And that's what's going on at this particular recursive call. So now we're at 3. Which element do I want to investigate first? Yes. 1, very good. So we got 3, its parent is 0, and now we're going to say 1, its parent is 3. So now we're here, we're going to put 1 on the stack. And so where do we want to go next? Which one do I want to choose here? Also, I'll bring up my Slack on the phone. Yes. 4, very good. Okay, I understand you. So 4's parent is 1. So now we get to 4, and there's nothing going on. So for those of you also on the Slack, I'll have my cell phone up here. Okay, C. So C is the correct answer. All right, so now we get here and there's nothing. So now what's going on is we're done with this recursive stack call. We were going to remove 4 from the stack, and now we're back at 1. So where do I want to investigate next? 2. So 2 has not been visited. So now what's going to happen is we're going to have 2 with its parent of 1. And now we put 2 on the recursive call. So 2, now I'm here. Now the crucial thing is, what do I do here? The next step is 1. What should I do? Do we investigate that? Why not? Yes. We've already visited it, so it's already here. And that's a crucial thing with depth first search. We want to basically find a path where we haven't encountered any new nodes, where we haven't encountered a same node twice, because we don't want to get what's known as a cycle. So then we do 1, which means we now go to 5. So now 5 has not been visited. So we put 5 here, and its parent is 2. And then we put a call to 5 on the recursive stack. Right, so this means that we're now going to do 7. 7's parent is 5. And 7 goes on the stack. We go here to 7. 7 has 8 as its first one. So now 8's parent is 7. And now we put 8 on the stack. Now we go to 8, and we see we have 5, which we've already visited, and 9. So now we put, see, 9's parent is 8. And on the question, we're saying we want to find the path from 8 to 9. So once we have found 9, that means we've solved our problem. Which means then we're going to go back up and down. We're going to remove everything from the recursive stack here. We go back down, and now what we have is our solution. So the way I would figure out the solution is I'd start at the solution here. If we found it, I'd say, now instead of a recursive stack, I'm just going to use a regular stack. So now I'm going to say, well, it's 9, and then that's 8. I go to 8, and that's parent 7. And I'm putting each one on a new stack. I go to 7, that's parent is 5. I go to 5, 5's parent is 2. I go to 2, 2's parent is 1. I go to 1, 1 parent is 3. 3's parent is 0. And then we hit our -1 sentinel, and now we have determined the path. So the solution is 0, 3, 1, 4, 2, 5, 7, 8, and 9. Does anybody have any questions about the process I used to determine that solution? All right, so what we're going to do next is I'm going to go back up to the coding, and we're going to code this together. So what I want you to do is I want you to go, well, first I'll walk through what it is that we're going to code so you can see the entire depth-first search algorithm at different levels of abstraction. And this particular search is from 4 to 30. And so first what's going to happen is I am going to go initially at 4. So we go there, we've updated that we have visited 4, and we say that 4's parent is -1. So those are the data values inside the nodes. So 4's has 2 outgoing edges. The first one in the adjacency list is 20, so we investigate that first. We then say that 20 has been visited and that its parent is 1. And we see here on the stack that this is this recursive calls. And so when we get back to here, let's say that 4 doesn't work, 10 doesn't work, and then we go through 30. It's all working at that specific recursive call on the instruction stack. So now we're at 20. Its first look is to 4, because we have a bidirectional graph in this case. We can't go there because it's already been visited. So now we're going to try 10. 10 has not been visited, so that's going to be updated, and we're going to make 10's parent 20. From there, we're now going to go to 10, so we now have 10 on the stack. 10 has outgoing edges to 20, 5, and 18. 20 has already been visited, 5 hasn't. So now we're going to say 5. We're going to update its visited verts, and 5's parent is now at 10. So now we look at 5. 5 has 2 outgoing edges, one's to 4 and one's to 10. So what's going to happen in this particular animation is we're going to see that 5 is going to be done. That's going to be pushed off the stack, and then we're going to go here. We don't have 4, we don't have 10. So now we're going to remove 10 from the stack, 5 from the stack, and we're now going to investigate the node containing the data value 10. So now we say, well, at this particular recursive call, I've already investigated 20 and I've already investigated 5. So now I'm going to investigate 18. So we checked 18. 18 has not been visited. So now we say that 18's parent is 10. And then we put 18 as our next recursive call. At 18, we first check 10. 10's already been visited. And then we check 30. 30 has not been visited. We now say it's updated, and we state that 30's parent is 18. And then we will go back up this recursive stack. We see everything goes away from on the recursive calls. And then the final solution, we start at 30. Then we say 18. 18's parent is 10. 10's parent is 20. And 20's parent is 4. So that's what we get the final solution. Does anybody have any questions about depth-first search and how we're using all these data structures that we've learned so far to be able to implement the potential solution? All right, let me also check the Slack to make sure that I haven't missed any questions there. Okay, should 8 be in the solution? 8, oh, you mean for over here? What's going on over there is because 8 had 5 and 9, what ended up happening is it went to 5, but in this specific case, 9 to 8, 8 to 7, because that's how we figured out the specific path towards the from the end to the beginning. All right, so what I would like you to do is, so this was time permitting from last lecture. So I want you to go to, in the code that you've downloaded, I want you to go to line 17 on graph 4.h. And when you open it, it will indicate that we are going to code a portion of the depth first search algorithm together. So what you're going to see in this file is a private depth first search method, and brings in a bool destination, an unsigned int for the vertex value, excuse me, a dynamic array that's called by reference, and we're going to use this to keep track of all the locations that we've previously visited, and as the bool visited as well. So we see that we have our two data structures that I've used. What I want to show you first is the public method that we use to set up everything. A lot of what's in the public method is design methodologies that you've already used in this class. So we're not going to code it again because it'll just be review. But what's going on here, I'm going to scroll down to this public method. And in the public method, first thing I'm going to do is I'm going to check to make sure, as we did last lecture, that the origin and destination does not exceed the thing that are being put in by the user does not exceed the size of the graph. And I'm saying, well, if vertices length is equal to 0, I won't be able to perform anything anyway. So if I get origin and destination is 0, and there are no vertices in the graph, we're not going to search. Then what I'm going to do is I'm going to initialize with a dynamic array, an unsigned integer for parents and booleans, just like I did over here. And then what I'm going to do is I'm going to create that stack that I used in the final step to be able to track down the solution. I'm also going to state that the origin that I received, that its parent is -1, which we're going to use as a sentinel to be able to ensure that we can go back and find the final trace. Then we set all the values of the visited dynamic array to false. Now I have another test. If I found the destination, if destin is equal to origin, then it's true. Otherwise, I just run the algorithm. So this one line of code, this is what we're going to focus on when we code together. So a bunch of stuff's going to happen, but we'll discuss. And the first thing is it's a Boolean. So if I'd never found it, there's no valid path from the origin to the destination. So now what I do is I set my sentinel to the destination, and I say, well, while the parent is not equal to -1, I push that onto that stack that I created, and then I update the sentinels. And then finally, I pop everything off of the stack to be able to produce my result. So what I want to do now is we're actually going to code up together the depth first search algorithm. And so I want you, if you're not already there, please go to line 17. And what I want you to do is we're first going to say that we need to say if we have not visited the vertex value. So if we have origin and I pass it to this value, I want to check, and we're going to make this recursive. So we're going to say if visited, a vertex value is not true. So if we haven't visited it, so visited is the vertex value. So if we haven't done that, then now we're going to do all the other stuff that we want to do. So first, I'm going to say, well, if it hasn't been visited, I'm going to set it equal to true. So if we've made this particular call, if it has been visited, we don't want to continue to make it an excessive recursive call. So that's what the if statement is there for. After that, we're now going to say, okay, we have visited it. And now this allows us to be able to iterate through all the vertices in this particular vertex. I'm sorry, outgoing edges in this particular vertex. So I'm going to say for, and we're going to say unsigned int iter is equal to 0. And this will allow me to iterate through all the vertices. So I'm going to say visited. I'm going to say iter is less than vertices vertex val. And if you remember, we have a private member, private method, num edges. I'm going to zoom out just a little bit, and then I'm going to say plus iter. So this would allow me to iterate through all of the edges. What you're going to see is that if I make the recursive call inside and we return true, meaning we have found it, we're going to break the for loop. So that way we don't have excessive calls. So the first thing we're going to do is I'm going to, for coding simplicity, we're going to say edge temp edge is equal, and how I get an edge from here is I'm going to say vertices at vert val dot get edge, and so this is a function, a method that we wrote, and I'm going to say iter. And so I'm going to be writing, we're going to write a few extra times here in the code where we would have to write that whole thing, but instead we're just going to have the specific edge. So that will be simplistic, and we're not going to change anything in depth first search, so it's perfectly okay that we're doing it this way. All right, so the next thing I would like you to do is we're going to say, well, if we haven't visited the destination, we're going to say if visited and temp edge.destin. So remember that each edge has a destination. So let me scroll down just a tad so everybody can see. So if we've already visited the destination, there's no reason to do this work. We don't want to investigate it. So we're allowing ourselves to do some safe programming here and safe traversals. So if we haven't visited it, then I'm going to say, well, the parents, so remember parents is this dynamic array. And now what I'm going to say is, all right, I have the temp edge as destination. So that's where I'm trying to go. Its parent is where I'm currently at. So what is the value that we're currently at? What is the representation for our current location in this code? Yeah, oh, no. Yes. Yeah, vert val, very good. So vert val is going to be the parent. So we're going to say temp edge.destin is equal to vert val. So that's equal to the vertex value. So Lydia correctly pointed out vert val as well on the Slack. So now we're going to say, well, if the temp edge destin, so now what we're going to do here before I finish this line of code, we're now going to check to see if this new destination, before we do anything recursive, is the destination. So we actually did this over here on the whiteboard. Once I found 9, we didn't do any more recursive calls because depth first search, we're searching for it and we found it. So if temp edge.destin is equal to destin, we are going to return true. And then finally, after doing all of this setting up, we're now going to do bool, and I'm going to call it check, is equal to depth first search. And so now let's take a look at the previous call and see what the values we want to pass. So we have our destination. So we always want to keep passing that so we can always check it on the next call. So destin is going to remain the same. What is going to be, so in the previous call, I called vert val. I want to pass the next vert val down to this recursive call. What should I write there? What am I passing to that recursive call? Where's the next edge I'm going to? Yes. I'm sorry, what? Yes, we want to go to the destination. So temp edge.destin, very good. Right. And so now we've got parents and visited, because we're calling these both by reference, which allows us to update them at that different level. And so last thing, before we go and we would iterate, so notice how this we are here in this if statement. The last part, before we would go back up here, is if we did find it, there's no reason, like if we've gone through 2 of 4 edges in the depth first search for that specific node, and we found, going down this depth first search, that we actually found the location. We found the node we're looking for. We don't want to keep going. So what we're going to say is, if bool check is equal to true, we're going to break. And what this piece of code will allow us to do is we're now going to take advantage of our knowledge of recursion. And what this will do is it will return true, and if we encounter it again, it will return true. If we return, it will just keep going and going and going. And that will be the case until we get to the top, and then we have our final stack. And so if we get through all of this, the last thing we should do, so I have a Boolean, and in this case, I've set it all up. I found one of the true cases. I found the other true case. What's the last thing I should do if I've gone through all of these particular edges and I haven't found anything there? What's the last thing I should do? To tell them I didn't find it, yes. Return false, outstanding. That's what Nikita was going to say, and I see that that's another comment in Slack about the same thing. So now we're just going to return false, and just so it's clear, it's after the if statement. So while everybody, I'll leave this here for a moment so that way you can continue typing or can review at home. So here's what this code is doing. We're making a recursive call, and first thing we do is we check to see if we have actually visited the edge. If we haven't visited the edge, we are then going to update and visit the edge. Indicate that the edge has been visited. And then we're going to iterate through. And if we haven't found that particular edge, we say that the parent is going to be true. Otherwise, and if the destination's here, we're going to say it's true. Otherwise, we're then going to make the recursive call. If a deeper recursive call finds this vertex that we're looking for, we're going to return true. Otherwise, if we got through all of the edges, it will return false. Does anybody have any questions? What does temp edge destin represent? It represents the destination of our edge that we created here. So we're iterating through each edge, and temp edge, I call this, so I get the edge at that specific iteration. So if I have 4 edges outgoing, so here's my representation, and I'm doing this 0, 1, 2, 3, and 4. If I'm at 0, when iter is 0, this value will be 1, like so. Does that address your question? Awesome. All right, so now you should be able to save this and update it. And then in here, you should be able to run make DFS. And what did I screw up here? No return statement at line 19. Returning non-void. Maybe you want to see what is possible I did. If not visited val, if. I think you have an extra semicolon. For loop here. Ah, there it is. Yes. Thank you, Matilda. You caught it. Oh, I have another problem. No return statement. So no, I didn't fix it. Did I update it on? No, I did. Oh, here we go. That should return false there. Any other theories as to what I might have screwed up? if check true. Why do we have to set visited val to true before the loop? So here, this is if we have not visited the edge, we need to visit the edge there. So this means that all that steps I did where I have on the whiteboard, if you look at the whiteboard over here, and I have that particular setup here where I have visited and parent, in order to do that, I have to know whether or not I've actually visited. So that's that particular edge. All right, so why do we have to set, oh no, that's the same thing. Visited val. All right, well, I'm going to move on and come back. I'll try this one last time, and then we'll come back towards the end of the lecture. I have to have a missing one somewhere. So the make DFS 2 wasn't going to work either. All right, so this is all the public stuff. Here's all the private stuff. Visited val is true. We check it. And there's all the correct code. So bool check. And so this is everything that we set up and did. All right, so what would come out is that we create this adjacency list representation, and then we see that the translation for 0, 1, 3, and 5. So these are the locations that we go through. We have path from 0 to 0 is valid. And then I have two other cases here inside of this piece of code where I'm passing get me to -1, and then 6 is 1 too many. So both of these are invalid. So the checks that I did at the beginning, so that's what's going on there. All right, so the other thing in 5, in graph 5.h, I've made some minor modifications. So here, this is the code that I was hoping to write up and work perfectly. What I have is this one was destined. And now what I do differently in so here I have the public method, death first search, and then I have another one here, where I have the same thing, except I take in the origin and the destination, right? So now, what I can do is if I'm doing depth first search 2, now this will work. Okay, or not. Oh. Did I update it? No. Clean. Well, it didn't update, so. So here's what's working. So now I see that I can update from 0 to 5, 1 to 5. There's no valid path from 2 to 4, which is what we want. And then we say from 3 to 5, there's just an edge there. So we see that from 3, I go straight to 5. From 4, 1 can go to 3, but then it also goes to 4. There is no valid path from 4 to 1. So I can go through the entire thing, and it's there. And I want to try one last thing. I'm going to press save, and I want to. That would be why. My apologies. So if this code is working for you, then the reason why is because I'm updating the wrong version of the code. So if I go to my test folder where I had everything, And so here's all the code that I wrote. Press save, update, and make DFS. If I get rid of this one as well, that will do it. Okay, so that runs, and then you should now have prob1 and prob2 text in there. And so several people in the Slack are pointing out that from what I type, it compiled, and so that was my error. All right, does anybody have any questions about any of the process that we went through on depth first search? All right, so now the next thing I want to bring up is, okay, so here's all the stuff there you can review too, is something called a topological sort. So a topological sort is depth first search, except I run it for the entire graph, and I returned the subgraph that contains all the vertices and the first time it's encountered through a depth first search. So what happens is I run the depth first search, and the algorithm is very similar. What I do is I create a copy of the graph, and then I just run depth first search, but instead of where I don't have that found, where I had that we indicated it was found and we stopped, we just don't stop. We just keep going until we've encountered every possible edge. And then what we'll do is we'll go and check the final edges, all the other edges, to see if we have encountered the graph. And the reason why is because there's a possibility, and this graph is a good example. So let's say I start at the node containing F. And if I start at F, then I will go to B. So B is going to be, actually I'll make this a thicker, here we go. So this is going to be part of my topological sort. Then I go to B, A is the first one there. So now I go to A, A's outgoing is C, and then we reach the end. So we would come back, then I would go to E, then I would go back to A, I'm done with all those edges, I recurse back up to B, B connects to G, like so. So now I go down to G, I have C, which has already been visited, and E, which has already been visited. So then I go back up to B, I've already visited that. Now I go back to F, which was my initial recursive call. We've done B, A, I haven't visited D, so I make that. And then I try to visit G, G has already been visited. So now we've visited every node except H. So H, we indicate that it's over here by itself. Now B has already been visited, so H is going to be in its own final topological sort by itself. Does that make sense? So that allows us to be able to determine whether or not a particular vertex is actually connected in the graph. That's going to be a problem that you're going to revisit over and over again when you take your algorithms course. So this is a problem that would be called a union find problem, and we're going to revisit that later this semester. So here is an example of a topological sort from the graph that I presented earlier. And the crucial thing is that if I were to run topological sort from 4 to 5 in the old graph and in the new topologically sorted graph, I will get the same answer. The edges that have been removed are superfluous. This means that we can use topological sorting to remove cycles from a graph. We're going to say I can do a topological sort. So let's say I had, I'm going to go back to the previous slide, and let's say I had, we start at F and F goes to B first, and let's say B goes to A, but then A went back to F. And then A, that was the first one here. What would happen is F would go to B, B would go to A, and then A would look back at F and say, well, I don't want that. We've already visited that. So then it can remove the edge from that particular graph. And this becomes very useful because we're now laying the foundations for trying to find the fastest path between two nodes. You may have noticed in our solution that this is not the most optimal way of looking for it. It's just a way we can prove and figure out that it's there. But what we're going to do now is we're going to work on the exact same graph, except we're going to see if we can determine its topological sorting. So to review, we don't want to check if we have found an edge because we want to try every single possible one. And that the result of a topological sort, now I'll show this when I run the compilation a little later, is that you can put in the search from an origin to a destination in the original graph and its topologically sorted graph, and you will get the same responses for all the searches. So what I want you to do next is I want you to run make problem 3. And what this problem has is it has adjacency list representation. It's the exact same graph. And what I'm going to do is I'm going to go over here, and we're going to work through it, and we're going to produce the topological sort based on the result. So I want you to take a couple of minutes, work on problem 3, see if you feel comfortable. And then what we're going to do is we're going to work through it together, and then we're going to see it in an experiment. All right, so what's the first step I should do here? I'm doing the same thing at the Slack up here on my phone. What's the very first step? Any ideas? It's very similar to depth first search. So what's the very first step we should do? Yes. Absolutely right. So we're going to say, all right, 0 is visited and its parent is -1. And so now we're going to start at 0 and our first one is 3. So what I'm going to do is I'm going to put 3 here and its parent is 0. So now we're going to move to 3. 3 goes to 1. Right? So now 1 has a parent of 3. Right? So the whole time we're working on this stack. So next, what I want to do is at 1, we have 4 and 2. So we're first going to start with 4. So 4 is going to be here, and its parent is 1. Right? So now we go to 4, and 4 is an end. So now what do we do? Yes. Go back to 1. Very good. So we're going to go back to 1, and we've already tried 4, and we haven't visited 2 yet. So now we do 2. 2's parent is 1. And now when we go to 2, this has, did I write this up correctly? Oh, I'll just go with this. All right, 1 and 5. So 1 has already been visited. And 5, can somebody please double check and make sure I wrote this correctly? Is that a 1 for the first place for 2 to go? And if not, please let me know. But we've already visited 1, so now we're going to do 5. 5's parent is 2. So now we look at 5, and 5 has 7 and 6. So with 7 and 6, we start with 7, and we say its parent is 5. Then we look at 7. The first one we go here is 8. So 8's parent is 7. 8, well, we've already visited 5, right? So 8 now goes to 9. So 9's parent is 8. So now what we have to do is we have to make sure that when we recurse back up that we haven't missed anything. So we're going to recurse back up. We've already hit 5, so now we're going to go back to the previous one, which is 7. So 7, 8, and 9 have both been visited. So now we go to 7's parent, which is 5, 7 and 6, and it turns out we haven't hit 6 yet. Does everybody see that? That's a crucial thing. If you don't understand that, please put up your hand. I'll explain that again. Okay, so now we have to say, well, 6 is here, and 6's parent came from 5, right? Yes. So then we go back, we go like, well, 6, 8, and 5 are there, so we can recurse back up and we find the entire thing. So what's our result? So we go through and we see that we have the initial graph. So 0 is 3, right? That's the only one that has the parent. So we want 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So now we're going to say, well, 1 goes to 4 and goes to 2. Does everybody see that? So the adjacency-less representation is still 4 and 2 here. When we go to 2, 2 is the parent of 5. So that's the one that's going to end up here. And now we go to 3. 3, 1, 2, and 5. 5's parent is 2. So 3 isn't the, well, 3 is the parent of 1. Does everybody see that? So 3 is the parent of 1. And this allows us to be able to figure all this out in terms of a topological sort. So from 4, 4 doesn't go anywhere, just like it's the original graph. From 5, 5 is the parent of 7 and 6. And so we have to keep it in the same order. Does everybody see that it's the same order there? So what I'll show you in the code in a moment is that we actually add the edges to the new graph. And that allows us to be, forgive me, I keep looking at my phone for the Slack and nothing's come up. So okay, I promise I'm paying attention to the lecture. At least one of us should be. Now we go to 6. 6 is not the parent of anything, right? 6 can go to 8 or 5, but 8's parent is 7 and 5's parent is 2. So this should be empty. 7 is the parent of 8. And 7 is not the parent of 9. So 8's here. And then 8 is the parent of 9. And so this is our reduced topological sort. We are able to reduce the number of edges and be able to figure out the path between any of the nodes. Does anybody have any questions about that? All right, so the next thing we're going to study is another search entirely. Okay, see, there's a couple of comments in the Slack. Or there are some people typing in the Slack. And so I believe that makes the answer A, and that's the correct answer. So can you repeat how I got the 6 in 5, 7, and 6? So over here, and I'm going to go back over, it should still be, for those of you on Zoom, I'm going to show up in that top right corner in a moment. So over here, what happened is 5 is the parent of 7, and 6 is also the parent of 5. So when we did our depth first search all the way through the whole thing, we got through to 5. It was initially 7, 6 here, and when we did it both times, that's how we got its parents were 5. So that's how we got the 7 and 6 in the final one. So Simran, did that address your question? Okay, awesome. All right, so the next thing is, I don't see any other comments in the Slack. We're now going to discuss a different type of search. Okay, so let's only show you graph 6 really quick. And what happened is, so I've alluded to creating a new graph, and this is actually going to return a new graph top sort. And then what I do is I make a copy of the entire, I make a copy of all the vertices. And see, I just get the vertex value. So that was a method that we wrote in the previous lecture, get vertex value. And now once we add all the vertices, we now set up the topological sort in the exact same way we did depth first search. We have the parents visited. I use that stack to do that final path, and we set up everything for the parents in the sentinel. Basically, after that, we just perform depth first search, except the only thing that's different, if I bring up graph6.h, which you have a copy of here, so top sort, is that instead of, I don't have any cases where I break. Does everybody see that? I go through every possible edge, and we just keep going, and I add the edges in the event that we have a topological sort. So then what happens is once that's done, what I will do, and so let me go down to topological sort for the public method. So what I do with the rest of it here is I call that method there. And remember I said call it for every single vertex because there's no guarantee that every vertex is connected. So that's why I have this for loop here that I've highlighted. And then from there, what I do is I get the edge value and the weight from the old graph, and then I add the edges to the topologically sorted graph. And the way that I know that is because in the return vertices, I have its parent and its destination. So I'm able to find the edge weight, add that, and then add those edges. And that edges that will be responded to, that will be our topologically sorted graph. So we say here, if we have a question, why is it that a vertex can be a parent of another vertex, but that other vertex isn't the parent of the first one? Shouldn't the edge connect both of them together? So that is the question that's posed by Connor is what happens when we have a difference between a unidirectional graph and a bidirectional graph? In this specific case, if we want to represent a bidirectional graph, we have to have an origin and destination one way and an origin and destination the other way. Think of it like a road. Like a road, if it's bidirectional, we have some sort of median strip or pair of yellow lines that allows us to be able to differentiate which way we're actually going. That allows us to know which way we can traverse on a depth first search or what we're about to learn about, which is a breadth first search. So we need that differentiation to be able to tell which direction we're going. Hey, Connor, please let me know if that addressed your question in the Slack. So here's all the code. There's the justification for the loops. And then what I'm going to do is I'm going to, in this topsort.cpp, I'm going to create depth first search. I'm going to create a graph. I run depth first search. Then I get the topological sort, and then I run depth first search in the exact same order. All right, glad to hear it, Connor, by the way. So what I'm going to do is in here, and you have this code available to you as well, I can run make top sort, and we see that with the original graph and the topologically sorted graph, I run the same algorithm, I run the same search, I run depth first search on both graphs, and it produces the same result. Does anybody have any questions on that? And then I've produced the original graph here in this particular diagram, and then the edges in gold are the edges that remain after the topological sorting. Wait, I thought I got rid of that. All right, so we'll cover shortest path algorithm on Tuesday. The next one is breadth first search. Now we've studied breadth first search before, and we're going to apply our knowledge of queues. So already we have, in this particular assignment, we've done dynamic arrays. So that shows us our knowledge of static arrays, which shows us our knowledge of memory allocation on the heap, which digs back down to void pointers. In order to use a stack, what's the data structure that a stack aggregates? Want someone to tell me that real quick to review? A linked list, specifically which linked list? Yeah, go ahead. Singly linked list. So now what we're going to do in breadth first search is we're going to use a queue, which aggregates what kind of linked list? Someone want to tell me? Yes, doubly linked list. And that's because we can add it at the back and then take elements off on the front because we have the head and tail pointer. So a good thing about graphs at this stage in the semester is that it is a good review of every other data structure. On Tuesday, we're going to do Dijkstra's algorithm, which is going to revisit priority queues. So we're going to use a maximum heap. So in order to do this, we have to use every single data structure we've learned up to this point. So breadth first search, basically, just like the depth first search, it kind of creates a tree. And what this allows us to do is it allows us to be able to figure out some sort of ordering. And we're going to use this when starting next Thursday when we go over binary search trees. And so here's what we learned previously in lecture 9. In lecture 9, we had this little tree, and I showed you this animation I'm going to repeat to you again. So I want to find a path from 1 to 8. So what I'm going to do is I initially put all the outgoing edges from 1 into a queue in the order that we encountered them. So that's 2, 3, and 4. And then what I'm going to do is the element at the front of the queue is what I'm going to evaluate next. But then notice how I put 5 and 6 onto the back of the queue. 3 is going to be the one that's next. So that queue aspect, by putting those in, that allows us to look at it as a more breadth approach. So a depth first search, think of it like if you're going through a corn maze. So if you have a corn maze, you only really know what's around you, and you investigate one way, and that's the next way to go. Breadth first search is more like if you're looking at a map. So if you're trying to figure out how to get to one place to another, and you know that these, or you can go, you're not really going to do all this investigation over here if you know that you can go this way with a breadth first search. So that's the difference. So now we're going to complete this. We take 3 off, and now we have 4, and one of the outgoing edges is 8. So what I'd like you to do now is we're going to take a couple minutes, and I want you to run make problem 4. And we're going to find this is the exact same graph, but now it's going to produce a different result for breadth first search. Ah, that's where it was wrong. Okay, has anybody figured out the answer? Yes. It is B. B is correct. So now let's work together and see why this is. So now I have the whiteboard up here. So now we're going to work through this and determine what's the difference between depth first search and breadth first search. So instead of having a stack, what I've done here is I now have a queue. So we're going to start at 0. And what elements are going to go into the queue and in what order to start? So what's the very first step? Yes. Yeah, we got to put it up in there 3, 1, and 2. So this is going to be 3, 1, and 2. And we had to say visited. And its parent is 0. So now we investigate 3. Anything that we haven't visited yet is put into the queue. So now we say, well, we visited 1, we visited 2, we haven't visited 5. So now 5 is put at the end of the queue. 5's parent is going to be 3. And then, now that we're done with 3, remove 3 from the queue. So now we're going to investigate node 1. We have not investigated 4, so we're going to put that at the back of the queue, and 4's parent is 1. 2, we have visited, so we're not going to investigate that, and now we can remove 1 from the front of the queue. 2 has 1 and 5, both of which have been visited. So now we can do that. So now we look at 5. 5 has 7 and 6, and neither have been visited. So we say 7's parent is 5, and 6's parent is 5. And then I put them in the exact same order. Then I say, well, 5's gone. I look at 4. 4 has no outgoing edges, so now we can remove that from the queue. And then we go to 7. 7 has 8 and 9. So we'll go through this process. And then what's going to happen is we are going to see that it ends here. So now I have the exact same scenario. So now I can just go backwards and do the same thing. I should put 0 and -1 there. So now I say 9 and 7. So I would say 9 and 7. 7's parent is 5. 5's parent is 3. And 3's parent is 0. And 0 has -1, and we have encountered our sentinel. Does anybody have any questions about that? Right, so with this information, let's say instead of stopping here like I did, what I want to do is I want to keep going. Right? So let's say I have 7 and 6. I've investigated 7, and then I do 6. So 7 is done, 8 and 9. Put it in that order. 6 has 8 and 9 as well. You go 8 goes to 5 and 9. And then 9 comes here. So now what I can say is, based on this information, that I have a different kind of graph, a different kind of directed acyclic graph. This time I'm going to use the origin and destination. So I have 3, 1, and 2 here. So for 1, 1 is the parent of 4. It is not the parent of 2. 2 is not the parent of anything. It's a destination. If we take breadth first search, we can't get from 2 to anything. Well, we started at 2, we 0, 1, and 5. When we start at 0, no path from 0 to any other node will go through 2. So 3 is the parent of 5 only. 4 is not a parent of anything. 5 is the parent of 7 and 6. 6 is not the parent of anything. It's another destination. 7 is the parent of 8 and 9. So we're going to put it in the exact same order. And then both 8 and 9 don't have anything there. So this is known. So the previous one for depth first search, that is known as a topological sort. Right. The other one, for breadth first search, this is known as a spanning tree. Has anybody, particularly if you remember from when I was talking about the breadth first search, I'm sorry, I was talking in the pre-internship, does anybody remember me using the term spanning tree? Specifically, does anyone remember me using it in the context of a particular mentor? Is anyone in here on the Dell project with Radia Perlman? Radia Perlman, her contribution, she used spanning trees to be able to do a protocol to be able to basically invent Ethernet. Without her, we wouldn't have been able to do this. The internet would never have gotten over probably 40, 50, maybe even 100, because it was just too complex. Getting rid of these edges here and being able to find the most breadth, the most computers that I can talk to from any given node without having cycles or superfluous communication, that was her major contribution. And so that is how we are able to do all these things that we're able to do today. Does anybody have any questions on breadth first search or spanning trees? What we're going to learn about on Tuesday is something called a minimum spanning tree, where we're going to weight the edges and figure out the fastest path. And then we're going to learn about Dijkstra's algorithm, where we're going to find the shortest path between two edges. So when we have edge weights, we want to be able to consider those searches. Like we have depth first search and breadth first search. Sometimes the depth first search is the fastest way. Sometimes the breadth first search is the fastest way. The shortest path algorithm will help us determine which one is which. All right, does anybody have any other questions? All right, so I'm going to go back up to the board. I'm sorry, up here. And basically, first up, what I want you to do, I'm going to share my screen, and if you run test.sh, so we've done the first 4 problems, it should say that you've earned 110 points today. And first I'll answer a question in the Slack, and then I want to ask you all a question. So the first question is, when would you use breadth first search over depth first search? It really depends on the specific application. Breadth first search, if we're using queues, we can use that to kind of come up with a breadth approach, kind of like what we were talking about with the spanning tree and Ethernet. Whereas depth first search allows us to come up with a maze appropriate Like if we put a mouse in a maze, for example, we could simulate that. Anything that simulates those type of behaviors is the difference. Right? Does anybody have any other content-related questions? All right, so I want to take the last 2 minutes of lecture. I'm going to do a stop share here, and I'm going to go over to one of the boards. And I want to ask how everybody's doing. How's everybody holding up? Like, as I know you got the systems exam. You had the systems exams yesterday, right? And when is your logic design exam? What? I'm sorry, what? Tuesday. Okay. Oh, Tuesday. All right. All right. So I'm trying to figure out the right way to do this because you all seem exhausted, and I have a coding challenge due that I can move around. That I have the liberty to do that. Do you all have anything terribly exhausting after your logic design exam? Anybody have any other exams, anything like that? So would anybody be heartbroken if I extended coding challenge 6 from due on Saturday to due, I'll give you at least 2 days. How about the normal Thursday night at midnight slot? Is that agreeable? If anybody, well, before I agree to that, I want to give it 24 hours. If anybody, because when I say that and everybody's nodding their head, there's always that one person who has a valid complaint, possibly, that is afraid to speak up. So I want to give anybody who wants to bring a concern to this plan that I've come up with, please let me know in private. I won't out you or tell you what anyone, so your classmates don't gang up on you. But if there is a valid reason I haven't considered, I want to make sure that I'm fair to the entire class. But judging by how everybody's nodding their heads, that's probably not going to be an issue. All right, so let me get back to you. I will send the message out tomorrow. It will likely include an extension to next Thursday. I want to make sure that I can, because you have an exam gauntlet, I want to be fair. You guys just look exhausted, so I want to give you a little bit of a mental break. And that way you can focus your work on the pre-turnship, because it seems like you all are really having a lot of fun doing that. So on that note, it is 2 o'clock and you all are dismissed.